The Doomed Cylinder, the observation and analysis of flow regimes over a circular cylinder in the CalPoly low-speed wind tunnel, by Giovanni, Aaron, Lauren, and Elena. This report presents the findings of a lab performed with the CalPoly Aerospace Department's low-speed wind tunnel that takes a look at the vortex street behind a bluff body and the drag of that object. The experiment was performed with a horizontal smooth cylinder attached to the inner walls of the wind tunnel, perpendicular to the flow. Also in this lab, the vortex street is altered by tripping the boundary layer to prolong the separation point. The purpose of altering the separation point on the cylinder is to compare the drag force on the cylinder with the prolonged separation point and without. Coefficient of drag is calculated from pressure ports on the cylinder. It was observed at higher velocities the coefficient of drag decreased when the cylinders and flow fields create flow regimes based on Reynolds number. Reynolds number under 5 produce creeping flow and no separation behind the cylinder. Higher Reynolds number will create a separation region behind the cylinder and therefore create a vortex street, which is an oscillating flow of shedding vortices behind a body, or cylinder in our case. Different flow regimes produce different patterns of wake vortices as shown in the figure to the right. Objectives of this lab are to grasp a better understanding of the flow vortex street and to see how it influences drag. To look at the flow vortex street behind our cylinder, we have to take slow motion videos, because in real time the high frequency of the shedding vortices will cause the vortex street to look like a solid wake. We will also be determining the pressure drag coefficient of the cylinder with 24 evenly spaced pressure points on the surface of the cylinder. Then to analyze the effects of the vortex street has on the drag, we altered the size of the street by tripping the boundary layer to delay the separation point. Based off the knowledge obtained in Dr. Doy's class, we assume that the tripped boundary layer will decrease the drag coefficient. When the boundary layer is tripped, the flow around the cylinder becomes turbulent and gains energy, which keeps the flow attached to the cylinder longer. With the separation point further back, the size of the drag inducing low pressure wake behind the cylinder will decrease. So with a smaller low pressure wake from the tripped boundary layer, it can be assumed that the coefficient of drag will lower. This concept is used when designing golf balls. The dimples on the ball trip the boundary layer to lower drag.
Methodology. 3 main sections make up the methodology: group member positions, test preparation, and testing procedures. Here we have a diagram of the CalPoly low-speed wind tunnel, which shows every main dimension and every section labeled by its name. Group member positions. For the cylinder of Doom Lab, the first steps taken in an effort to determine pressure and drag coefficients of the circular cylinder included very fundamental preparation procedures, starting with the documentation of lab conditions and assigning of vital tasks for each group member. These tasks included the handling of the laser for smoke visualization from front to back of the cylinder, handling of the smoke machine to assure direct smoke contact with the cylinder, overseeing and operating the wind tunnel, along with LabVIEW using MATLAB to ensure stable data collection from the sensors on the cylinder at different RPMs, and taking pictures and videos of the interaction between the smoke and the cylinder for visual analysis of the flow separation at each wind velocity. Here, every position is labeled and shows where exactly each task took place. Prior to activating the wind tunnel, we took measurements such as port locations and cylinder diameter to map out the flow around the cylinder. It was important to note that ports 2 through 25 were the ports on the cylinder and that port 11 was located where stagnation pressure on the cylinder took place. After the team confirmed that the pressure ports were connected and working, the proper safety procedures posted in the control room wall were followed to ensure that the experiment would run safely with minimal error. Since we were trying to evaluate and differentiate pressure coefficients, drag coefficients, and Reynolds numbers for the cylinder based on surface roughness, we started by using the smooth surface of the cylinder itself. We began official testing after measuring static conditions by ramping up the wind tunnel to 50 RPM while the smoke and laser were activated so that we could also begin flow vis using phone cameras. The main goal was to record and observe the effects of smooth surface of the cylinder at 50 RPM and then repeat this with the 400 and 600 RPM tests. The reason for this range of RPMs comes from the idea that at different wind velocities, the flow pattern of the cylinder would change as Reynolds numbers would change as well. In order to achieve surface roughness for aerodynamic appeal, we had someone place the tripping wire at 45 degrees from the horizontal of the cylinder and repeated the same procedures as before. Each group member kept their positions and LabVIEW continued to be analyzed with MATLAB for each test, which allowed new numerical data that represented the rough surface of a cylinder to be visualized and gathered for comparative analysis with the smooth surface.
The wind tunnel velocities were determined based on Reynolds number and the flow regimes they represented. The lowest velocity case corresponds to a laminar boundary layer case, while the other two velocities relate to transitional Reynolds numbers. In all of the plots, the blue sinusoidal curve represents the ideal creeping flow approximation for flow around a cylinder. The approximation takes this shape due to the presence of a stagnation point with maximum pressure at the front of the cylinder, resulting in a coefficient of pressure 1 at this point. In an ideal world, there is another stagnation point at the back of the cylinder where the pressure coefficient returns to 1, creating the sinusoidal shape shown. However, when creeping flow does not occur, the flow separates from the cylinder and doesn't reach the second stagnation point. The wake formed by the flow separation has a lower pressure and creates the shape shown on the red curves, which are data collected during this experiment. The error bars in the figures represent the standard deviation of the data to show how spread the data was around the average values shown. The error bars are greater at lower velocities, likely due to the effects of background wind not generated by the wind tunnel. The pressure coefficient profiles for all of the cases show a similar shape with slightly different values. For the slow case, the flow appears to differentiate from the ideal case sooner, meaning that separation occurs earlier. However, the pressure behind the cylinder is greater than that of faster speeds. This means it is closer to returning to a stagnation point behind the cylinder despite its early separation. According to Sengel and Simbala in Fluid Mechanics, Fundamentals and Applications, flow separation occurs on a cylinder at approximately 75 degrees for laminar flow and around 140 for turbulent flow. The laminar approximation at the lower Reynolds number appears to separate much sooner than the two transitional cases. However, the two transitional cases appear to separate before 140 degrees expected for turbulent flow. The two transitional cases have very similar pressure coefficient profiles due to their similar Reynolds numbers. The pressure coefficients determined around the cylinder with a tripwire were compared to those with no tripwire to determine if delayed separation has occurred. In the two transitional cases, the flow behind the cylinder has a higher pressure and appears to more closely follow the creeping flow approximation, dipping to lower pressures at the top and bottom of the cylinder and increasing in pressure behind the cylinder. The lopsided dip in pressure coefficient that is consistent on both figures is likely due to the trip strips being placed at an angle to the length of the cylinder. For the laminar case, the pressure behind the cylinder has decreased, instead of increasing like the other two cases. The profile does appear to more closely follow the creeping flow approximation around the surface of the cylinder, leading to the assumption that the separation point has been delayed. However, the pressure behind the cylinder has decreased. The tripped pressure coefficients at this velocity more closely resemble those of the transitional profiles. It is possible in the low Reynolds number case that tripping the boundary layer caused the flow to become turbulent or transitional instead of laminar, resulting in the lower pressure behind the wake region. Using an approximation of the cylinder as a polygonal prism with 24 sides, the same number as the ports, and assuming that the ports are in the center of each of the sides, pressure drag and lift coefficients have been approximated for the cylinder in all of the cases tested. Putting the pressure points at the center will cause errors due to the stagnation pressure accounting for a much larger area and the pressures at the top and bottom being excluded. The pressure drag coefficient for the laminar case acts differently to the two transitional cases, increasing with the addition of a tripwire. It is possible that the flow was tripped too early in this case, causing the separation to occur early and therefore increase the drag felt by the cylinder. The two transitional cases decrease their drag coefficients with the addition of the tripwire, supporting the conclusion that the turbulent boundary layer will have a separation point further around the cylinder, decreasing the pressure drag felt by the cylinder as the wake is smaller. According to Sengel and Simbala, the theoretical value for coefficient of drag for cylinder in turbulent flow is 0.3 and for laminar flow is 1.2. The drag coefficients calculated most closely resemble that of the turbulent flow. The drag coefficient with no trip in the slow case is much lower than the other two drag coefficients. This is likely due to the drag at lower velocities being mostly due to the skin friction drag, which was not calculated in these values. The skin friction drag would increase the drag coefficients for all of the cases, but would more significantly affect the lower velocity case. Due to the symmetry of the cylinder and the flow, it is expected that the coefficients of lift in all cases will be 0. The slight errors making the lift coefficients not 0 could be due to the inconsistencies in the free stream flow and the cylinder not being accurately lined up with the stagnation point, pointing directly into the flow.
The purpose of the flow visualization was to give students a better idea of what is occurring with pressure data. Similar to the analytical data, 3 speeds were selected to match analytical data: 1 meter per second, 16 meters per second, and 25 meters per second. In half of the data, a tripwire was added to the cylinder for half of the data collection. The thickness of the tripwire is 1.6 millimeters, and it was placed at a 45-degree angle from the center of the cylinder, facing the inlet of the wind tunnel. The flow visualization, from now on referred to as flow viz, and these slides represent the flow viz collected at 1 meters per second, which is approximately 50 RPM. The video on the left is the flow viz at 1 meter per second with no tripwire, where the video on the right is at 1 meter per second with a tripwire. According to Figure 2, there are two different flow regimes in these videos that can be observed. At first, in both of these videos, an unseparated flow regime is demonstrated, which is known as a laminar flow, and as the flow leaves the cylinder, the turbulent flow occurs, which is observed by the vortices that form off the cylinder as they move toward the end of the wind tunnel test section. In the flow viz for 16 meters per second, you will observe that the videos are in slow motion toward the end so you can get a better understanding of what the flow looks like. In this case, the 16 meter per second video without a tripwire, we observe that the vortex regime is laminar. This is a reference from Figure 2. In fact, this matches almost exactly what the flow should look like. However, if you look at the flow viz where the tripwire is inserted, you see that there is less of a distinct form of flow. This occurs because the boundary layer is tripped earlier, which means that it cannot retain the same type of flow than if it did if it was without a tripwire. Finally, at the fastest speeds, the flow visualization abandons the turbulent flow, and we see a regime of unseparated flow, which is most observable in the 25 meters per second without a tripwire. In the flow viz of the tripwire, a larger wake is observed because the boundary is separated earlier than that of the non-tripped wire, which causes a flow that resembles turbulent but is not quite due to the lack of vortices. Visually, it was seen that there is a distinct difference between using a tripwire to trip the flow and watching the natural flow occur. It is also notable that there is a difference between the flow at different Reynolds numbers. The data and the flow viz support the concept that adding a tripwire to cause turbulent boundary layer earlier will delay the separation of the flow.